The next type of exponential application we're going to see is something where we're using a relative growth or decay rate. Just be careful that relative rates are different than just if you have a regular growth or decay rate. It has its own formula that's kind of similar to PERT. All I did was change that P to an A because P stands for principal and we're not necessarily dealing with money. But we do have a relative growth rate or decay rate. If that rate is for growth, we're going to have a positive value. If that rate is for decay, we turn it into a negative value. So in example 1, a tumor is injected with 0.5 grams of iodine, which has a relative decay rate. So anytime you see this, I would underline or highlight, circle, whatever you can, that relative decay rate of 1.15% per day. We're going to write out this iodine function. So it says I of t, which means our input is t, our output is I, the amount of iodine. A represents that initial amount. We initially had 0.5 grams, so 0.5 E. And the rate is a decay rate. That automatically tells me that we need to make this a negative value. So it's going to be e to the negative 0.0115 based off of converting that to a decimal per day. So that would be t days. There's our function rule. Now we can estimate the amount present after 10 days. So I of 10 here is 0.5 e to the negative 0.0115 times 10. We just put that into our calculator. So 0.5 e to the negative 0.0115 times 10. I get 0.446 if I round it up. So I of 10 is 0.446 grams. C says, determine the number of days required for there to be half the initial amount present. Since we know the initial amount, I can take half of that. Well, half of 0.5 is just 0.25, if you didn't know that. All right, so 0.25 equals 0.5 e to the negative 0.0115 t. We're solving for t, which means we need to isolate our exponential. Get rid of the 0.5. We get rid of it by dividing, since that's currently multiplication between them. So we divide by 0.5. .25 divided by 0.5 is just 0.5. So I have e to the negative 0.115 t still. I convert to a logarithmic form. That logarithmic form is base e, so it's a natural log of 0.5 equals negative 0.0115 t. And let's just put that back up here so I have room. If I divide by t, or not by t, divide by 0.0115, I'd have the natural log of 0.5 divided by negative 0.0115. Let's put that in our calculator. So natural log 0.5 divided by negative 0.0115 is roughly 60.27. And when we think about what does that represent, t was the number of days, so 60 days to be half the initial amount. Number 2 has the population of a small town is growing exponentially. It was 15,500 in 2018 with a relative growth rate of 4.7% per year. So if I write out P of t, it was initially 15,500. E, I know I'm using E because it said a relative growth rate and not just a growth rate of 4.7%. So E to the 0.047 t. Notice I didn't make it negative this time, and that's because we have a growth and not a decay. Determine the projected population in 2025. So think back to years. If 2025 is the number of years after 2018. If you need to subtract that, you can. 2025 minus 2018 is just going to be 7. But we're talking about 7 years later, so t equals 7. That's how we work through that. P of 7 would equal 15,500 e to the 0.047 times 7. So 15,500 e to the 0.047 times 7 is roughly 21,538.46. We're talking about populations, so we can say in 2025, the projected population will be approximately 21,538 people. So I didn't include the decimal just because we're talking about people. In what year will the population be approximately 40,000? So this time I'm solving for the year, and we can make that a y instead of a p of t, but 15,500 e to the 0.047 t. We know we're looking for 40,000, so y is 40,000. That's what I should have put there. To isolate t, we need to undo this multiplication, which means I need to divide by 15,500. You can put that in your calculator and get that decimal or fraction. So 40,000 divided by 15,500 is 80 over 31. You do want to try to keep it exact because you don't want to round within your problem. But when I convert to a natural log, because I'm going to have a log base e, inside that natural log would be that 40,000 over 15,500, or 80 over 31. It's equal to 0.047 t. We divide by 0.047, so t in my calculator would say natural log of 80 over 31 divided by 0.047. But that's approximately, let's see, natural log of 80 over 31, close it out, divided by 0.047, so 20.17. If it's asking in what year, it didn't want us to say 20.17. That's how many years later we have. So if we started out with 2018 plus 20.17 years would be in 2038, the population will be approximately 40,000. So if you see something that's talking about a relative growth rate instead of just a growth rate, you want to use this type of equation.